Hello friends. So the next lecture in my lecture series is which compound can be called as an organic compound. So as we have seen in our earlier lecture that organic chemistry is a chemistry of carbon compound. In today's lecture we will try to answer which compound can be called as an organic compound and which compound can be called as an inorganic compound. If you have a look at the periodic table, you will see out of 118 elements so far in the periodic table, the chemistry of carbon compound is called as organic chemistry, whereas the chemistry of other compound, it is called as inorganic chemistry. If you see the periodic table, you can see that this element alone, it is producing millions and trillions of compounds every year. I mean, there are about million and trillions of new organic compounds synthesized every year. On the contrary, the rest of the elements, means other than carbon, you will notice that only few lakhs inorganic compound are there. So because of this clearly indicates how organic chemistry is important. If you look at this periodic table, you will find that these are the elements which are highlighted in this periodic table. You can see that this carbon can form a bond with varieties of the compound and the varieties of the elements, and those elements have been mentioned over here. All other elements in the periodic table, they have kept blank here. So you could see these if one has a focus on how does a carbon bond form with these elements and what is the kind of the reactivity of these compounds, one can have a better command on organic chemistry. You can see that carbon is a very, very important element so far as organic chemistry is concerned, or it is a central element to all the organic compound. My point is, what makes carbon so special? It has been playing a central role in all living organisms, as has been rightly pointed out by Berzelius, that all the living organisms, they produce some organic compound, or some organic compounds are involved in the metabolism of the metabolism of the living organism. And this particular concept of vitalism that has been given by Berzelius, one can easily point out that the carbon plays a central role in all the living organism. It could be your carbohydrate, it could be protein, it could be amino acid, it could be vitamins, it could be anything else, it could be enzyme, it could be any metabolite that is involved in the metabolism of a living organism. Carbon plays a central role. Now, what makes carbon so special? If you have a look at the electronic configuration of the carbon, you will notice that it has got 4 electrons in its valence shell. That gives an additional advantage to the carbon, that it can form 4 covalent bonds. And the interesting feature of the carbon is it loves to form a bond with any element, and it really loves to form a bond with other carbon atom, making long chain. It can form bond with various other elements that we will see soon. If you compare carbon with other elements, particularly you can compare it with hydrogen, which has got 1 valence electron, can form 1 bond only. You can compare with oxygen, which can form 2 bonds as it contains 2 electrons in its valence shell, unpaired electron in its valence shell. And you can see nitrogen atom, which can have 3 valence electrons in its valence shell, can form 3 bonds, and carbon, as already been discussed, has got 4 valence electron and can form 4 bonds. So this is the beauty of the carbon. Why carbon is so special can be rightly seen from the outer electronic configuration of the carbon. If you have a look at what carbon can, with which element the carbon can form a bond, you can see that, as already been mentioned, carbon being central to the organic chemistry, carbon, it loves to form a bond with another carbon atom, leading to the formation of chains of the compound, and leading that property of a carbon is being popularly known as catenation property. So carbon is the only element in the periodic table which is using its catenation property to form a series of organic compounds. What else it can do is it can form a bond with hydrogen, leading to the formation of hydrocarbons, which is again an important class of an organic compound. Whatever the fuels we get, like benzene, petrol, diesel, kerosene, these are all hydrocarbon. We usually call them as a petroleum. I would like to make the word petroleum clear here. If you split the words, what I have noticed, if you split the words, petra means rock, oleum means oil. So petroleum means rock oil, which can be obtained from the earth crust. Another element with which carbon can form a bond is nitrogen, which is very next to the carbon in the periodic table. It's a 15th group element. Carbon can form a bond with nitrogen, leading to the formation of various amines, imines, cyanide. And it is important to note that being a student of organic chemistry, should look at how many bonds can be formed between the two elements. So you can see carbon can form, there can be a carbon-nitrogen single bond, there can be a carbon-nitrogen double bond, there could be a carbon-nitrogen triple bond, as in case of cyanide. Next element in the periodic table with which the carbon can form a bond is oxygen. With oxygen, it can form two bonds. It could be a carbon-oxygen, two types of bond. One could be carbon-oxygen single bond, other could be carbon-oxygen double bond. The same is applicable for the other elements in the periodic table. Particularly, if you compare nitrogen, then the similar chemistry would be shown between carbon and phosphorus. If you compare the other elements from the oxygen family, particularly sulfur, selenium, tellurium, very less compound, organotellurium compound, there are very less organic organotellurium compound, but still similar kind of chemistry can be shown by the other elements in a group. It can also form a bond with halogens. So halogens, we have seen that they can form one bond. So carbon can form a bond, carbon can form a single bond with the halogen. In addition to this, carbon can form a bond with some metal like lithium, leading to the formation of organometallic compound. You could see this periodic table, this organic chemist periodic table. You will notice that carbon can form a varieties of the bonds. It can form a bond with carbon, carbon with nitrogen, carbon with oxygen, carbon with halogen, carbon with metals. Few metals which are of importance in the organic chemistry is organolithium compound like methyl lithium, n-butyl lithium. Then it can form a bond with sodium. Particularly, you can cite an example of an sodium acetylide in particular, which is formed in situ. With magnesium, the well-known Victor Grignard's reagent. You can see some organopotassium compound, which is very less. Organocopper, organozinc. Likewise, carbon can form bonds with various elements in the periodic table. What is important point that is to be noticed over here, or that could be emphasized over here, is what carbon can do with different elements. One should be able to count out how many number of bonds a carbon can form with a particular element. Here what I am trying to do is I am trying to list out the various functional groups which are present in the organic chemistry and how carbon forms different bonds with different elements, and that results in the formation of various functional groups in the organic chemistry. So you could see, if you compare it with oxygen, when a carbon bonds forms with oxygen, what will happen? You could see carbon when forms a bond with oxygen, it could be a carbon-oxygen single bond, it could be a carbon-oxygen double bond. If you see a carbon-oxygen single bond, you will notice that carbon-oxygen single bond could be of an alcohol, means there is a COH functional group present there. It could be of phenol, if carbon is a part of an aromatic ring. It could be some ether, if oxygen is bonded to two carbon. Similarly, carbon can form a double bond with oxygen, leading to the formation of varieties of the carbonyl compound, which includes aldehyde, ketone, ester, carboxylic acids, amides, acid chlorides, etc. Similarly, carbon can form a bond with halogen, leading to the formation of halogen derivatives of the carbons. Next point is, where does inorganic chemistry ends and organic chemistry begins? Which compound can be called as an organic and which compound can be called as an inorganic? To answer this question, I have a few examples with me. The antiviral forscamate, it was an organic compound. It has a formula CPO5Na3. It has no carbon-hydrogen bond. This is an antiviral agent. Is it an organic compound or an inorganic compound? Because we have seen in the definition of organic chemistry, the compounds of carbon, they are called as organic compound. And we have seen what are the exceptions there. You can cite the examples of carbon monoxide, carbon dioxide, then the carbides, then cyanides, carbonates, bicarbonates. These are the few examples of carbon compound which cannot be classified under the category of organic compound. So the question that is left with this molecule, it has got only one carbon in it. Now the question is it an organic compound or an inorganic compound? Next example that I would like to cite is a very, very popular reagent, tetrakis-triphenyl phosphine palladium. This particular catalyst, it has revolutionized the organic chemistry. The invent of an cross-coupling reaction, particularly coupling reactions, cross-coupling reactions. I hope it is one of the most wonderful discovery of this century. So this particular compound, if you look at the molecular formula and the molecular structure of this molecule, you will notice that there are 12 benzene rings which are joined to the phosphorus and they are arranged in a square around the center palladium atom. If you look at the number of carbon, it has got 72 carbon and a significant amount of hydrogen. There are 60 hydrogens in the molecular formula of this compound. The question again remains unanswered. Is it an organic compound? Many people believe that it is an inorganic. Regarding the palladium chemistry, I would like to make this point very clear to the student that, as I already mentioned, that palladium chemistry palladium catalyzed cross coupling has revolutionized the organic chemistry. It allows to form the bond between carbon-carbon and carbon and heteroatom in particular. So those bonds which cannot be formed by using the routine chemistry, they can be formed with the help of a cross-coupling reaction. And many of you might be knowing that palladium-based catalyst has been a central to these coupling reactions. Now, my question is are these two compounds organic or inorganic? I have chosen these two compounds in particular because these two compounds, the first one contains 1 carbon, the second one contains 72 carbon. But still, the question is whether these two compounds are organic or inorganic. This question remains unanswered. And my answer to this question is we don't know and even we don't care. Because it is important these days to realize that strict boundaries between the traditional discipline are undesirable and meaningless. When I was a student, I have seen the professors who strictly say that I am from organic chemistry, I am from physical chemistry, I am from inorganic chemistry. But I have seen many professors these days who did their masters in organic chemistry, did their PhD in inorganic chemistry, and now they are teaching and doing research in physical chemistry. So as such, when you go up, you will find that there is no practical boundary, there is no actual boundary between these disciplines of the subject. In fact, and that has resulted in the development of what is so called as frontier sciences. So in the frontier sciences, you won't see any boundaries between the sciences as such. So we don't need to care about we don't need to know and we don't need to care whether a particular compound is organic or inorganic. What should be a role of a student, or what should be a role of a researcher, or what should be a role of a teacher is to understand the subject and how that subject could be beneficial to the mankind. In today's lecture, I will also try to cover few organic molecules of importance. You could see I have covered few different molecules. I have picked few molecules, and these molecules, they are somehow related to the lives and the lives of the mankind. So you could see my first example is of cis-retinal. Cis-retinal, this is a compound which absorbs light when we see. It is related to the vision. It is present in the retina of eye, and it is responsible for the vision that a particular man can see. There has been a mechanism of vision we suggest that there occurs some sort of cis-trans isomerism. So here comes the role of an organic chemist. What factors will bring about the cis-trans isomerism? Or in better word, one should know which isomer could be called as cis, which isomer could be called as trans. These are the things that a student should know. And another interesting feature of this molecule, retinal, is you need to find out the functional group in this molecule. So you could notice that there is a 6-membered ring with a double bond. You have few double bonds. You could count the number of double bond: 1, 2, 3, 4, 5, and 6. So you could see there are 5 carbon-carbon double bond and 1 carbon-oxygen double bond in this molecule. And you could see this molecule can, if you couple this molecule twice, I mean removing that oxygen and then coupling it together, it could lead to a formation of a new molecule which has got 11 carbon-carbon double bond. And that molecule is called as beta carotene, which is present in carrot. That is why our parents and our ancestors used to suggest that if you don't want to have the problem of night blindness, which has been associated with the vitamin A, which is retinal, so one should have an intake of carotene. That means carrot. Another molecule that I would like to cite here is a menthol, which has been commonly used in our houses on many occasions. So look at this molecule, menthol. Menthol, you would see, as a student of an organic chemistry, you should be able to look at the molecule, look at the functional group which is present in the molecule. So which functional group is present here? You can certainly see an methanolic OH, secondary alcoholic OH. And as is reflected in its name also, the name ends with the 2 alphabets OL, which means ol. So it clearly indicates that it is an alcohol. Another molecule which I have mentioned in my previous lecture also, quinine, which is a best known antimalarial, or the first antimalarial that has been used since the ancient times. You could see in this molecule you could have, apart from carbon and hydrogen, the heteroatoms present in this molecule is oxygen and nitrogen. Another interesting feature of this molecule is you could be able to locate the 2 oxygen which are a part of 2 different functional groups. One is a part of OH, which is a secondary alcoholic OH group. On the contrary, the other is OMe, which is an ethereal functional group. Again, you can see the 2 nitrogens in the molecule. One is a part of an aromatic ring, and other is a part of a tertiary nitrogen functional group. Another molecule that you could see, these are few molecules of very, very important. Usually you will come across this molecule: benzene, pyridine, phenol, aniline. These are the examples of the few aromatics with some simple functional group. You can add the example of chlorobenzene over here, and these molecules, they find varieties of application. To mention a few, phenol and aniline has been very widely involved with the dyes industry, resulting in the formation of an azo dye. These 2 candidates, propane dithiol and 4-methyl sulfanyl pentane 2-one, these 2 candidates, these are very worst smelling organic compound, and I wonder if somebody wants to find out who is the winner. So organic chemistry can offer you everything, something which is very sweet in smell, something very foul in smell, something very worst in smell, something which is very which you can test, which can test good, something which can test worst. Organic chemistry has everything to offer. See, again, an interesting molecule. This particular molecule is responsible for the smell of roses. So in my earlier example, I was talking about the worst smelling compound, and here I am talking about the smell of roses. This is an organic compound which contains SH, but this compound is regarded as a flavoring principle of the grapefruit. This is again a very interesting molecule. This is conjugated linoleic acid. This particular molecule, it is a conjugated linoleic acid, and it has been recently used as a dietary anti-cancer agent. That's why I tell organic chemistry has almost everything to offer. So you can use organic compound as an anti-cancer agent also. Now the next, another interesting pair of molecules that I would like to cite over here are these 2 molecules. Just now I told you that amines, I have shown you in the previous slide, I have shown you aniline. So So here you could notice this particular molecule, which has got an diethyl amino functionality in the aniline. This is a colorless aromatic amine. This undergoes some photochemical reaction in presence of an silver, resulting in the formation of an quinonoid form of the compound. These two candidates in particular, the first one which I have mentioned over here is an diethyl amino aniline. This compound, this converts into its quinonoid form. Have a look at that position of the double bond. In the first structure you could see it's a complete 3 double bond which are in conjugation, part of a ring. So such a structure is called as benzonoid structure. On the contrary, it gets converted into a quinonoid structure which has somewhat resembles with parabenzoquinone. So you could see 2 double bonds at the para positions and 2 double bonds in the ring, and they are not conjugated as such. Now what happens? This amino compound, when it reacts with a colorless cyclic amide, so we are trying to see one more amide, one more functional group here, amide functional group. When these two get combined, see, this is the beauty of inorganic chemistries. And when you mix 2 compounds, sometimes you get a very wonderful color. So when these 2 compounds, they are combined together, it results in the formation of a magenta pigments. So that is the beauty of this reaction, that 2 colorless compound, one which is activated photochemically in presence of silver, and the other is a colorless cyclic amide. These 2 combine together to form a magenta pigment, and that is responsible. This is how the color photography has been developed in the past. So that's all from now. I hope you enjoyed my lecture. If you like my lecture, do subscribe to my YouTube channel, Hsc Chem Hub. Thank you.